everyone, welcome to the next session of Finite Element Analysis. I am solving question 15 of Direct Application of E.M.E. Here I am going to start with Truss Element Analysis. Analyze the truss completely. The cross-sectional area of each member of truss is 100 mm square. Modulus of elasticity E is 200 gigapascal. This is a truss element that is given to me. The first step is discretization. Now this is the question given to me. When you are solving, you are obviously going to recreate the diagram. So I am not drawing this diagram again for discretization. Rather I am just discretizing this diagram itself. Here I can see element 1 and 2 is already marked for me. So I can say element 1 is between node 1 and 2 and element 2 is between node 2 and 3. Now for truss element we are going to assume 2 degree of freedom. 2 degree of freedom means there will be two axes x and y for our reference. So we are going to also mark the nodal values here. First node will have x1 y1, second will be x2 y2 and third will be x3 y3. Here let me start by assuming that node 1 has coordinates 0 0. You can assume this or this also as 0 0 and accordingly mark the other nodes, but it is always preferable to go for a corner node and then solve the other one. So I am using this as 0 0. Now from here to here I am going to walk along the x-axis by a distance of 300. So this will be 300 and I am not going in the y-axis, so y-axis value is 0. Now assume again you are standing over here. From here to this point, now obviously these two nodes are at the same level, so I am going to walk from here to here. There is no change in the x direction, only there is a change in the y direction. So the coordinates here will be 0, 400. So the degree of freedom is something which I am going to mark over here. For the first node it will be 1, 2. For the second node it will be 3, 4. And for the third node it will be 5, 6. So these are certain things which I am supposed to mark while going for the discretization diagram. Next I will go for step 2, which is development of E.M.E. Now when you are solving for truss element, there is a table which is supposed to be made. I will just show you quickly how the table is supposed to be made. First I will go for element number, which I will write over here. Next I'll go for nodes. Every element will be between two nodes, so let me call them as I and j. Next I'll go for its coordinates xi, yi. I'll have xj, yj. These are the coordinates of each node. Next I'll go for the length of each truss element. I'll call it as L. Next I'll go for calculation of certain terms, that is L, M, L square, M square and Lm. Now these are the terms that I'm going to require while making my E.M.E. So I am going to write them here. Now we are supposed to fill up this table. Now for that, first I'll write down element number. Now here you can see my first element is 1. So I'll write over here element number 1. Element 1 is between two nodes. The I node will be the left node, so I call it as 1, and the second node is the right node, which I call it as 2j. Node number j, which is 2. So first element is between node 1, 2. Now xi, x and y are the coordinates. I is indicating the node number. So when I talk about the first node x1, y1, I can see I have already written the value here, so I'll write down 0, 0. J is indicating this node number, so here it will be x2, y2. I can see x2, y2 is clearly 300 and 0. Now next I need the length L, which is already mentioned over here 300. So I need not calculate, I'll directly write 300. Now there are two formulas for calculating L and M. L is given by xj minus xi upon capital L. And M is given by yj minus yi upon capital L. So when I am solving over here L, it will be xj minus xi upon capital L. So it is 300 minus 0 upon 300, which will make it 1. When I am solving for m, it is yj minus yi upon L. Here it is 0 minus 0 upon 300, which makes it 0. Next calculation is very simple. L square of this number is 1, m square is 0, and L into m will make it 0. So this is the entire calculation for first element. Now I have one more element, so I'll write over here 2. If you see the diagram, second element is between node 2 and 3. So I will write over here element 2 is between node 2, 3. X, I, Y, I. So when I have I as 2, it will be X2, Y2. I know X2, Y2 is 300 and 0. So I'll write 300, 0. J is 3. So this will be X3, Y3. The value is 0, 400. So I'll write here 0, 400. The length of this element is not known to me. But if you look carefully, if this would have been a straight element over here, this entire thing would have become a right angled triangle. So I can use Pythagoras theorem for calculating this length L. So 400 square plus 300 square is equal to this length square. So the value of this length will be 500. Now I am supposed to calculate L. The formula is xj minus xi upon L. So it is 0 minus 300 upon L, which is 500, which will be minus 0.6. When I calculate m, it will be yj minus yi. So 400 minus 0 upon 500 will make it 0.8. L square will become 0.36. M square will be 0.64, and L into m. Very careful, there is a negative sign here. This will be minus 0.48. So this is a simple way of making this table. This table is important. We are going to make use of certain values from here, especially the length and these values. So let's go for writing of the EME now. The EME for truss element is given by AE upon L. Here the formation is something very important. Be very careful. Here we can just make a cross sign in between. Here you will have 4 elements, 4, 4 and 4 elements. So this is something which you need to remember. Here the terms are L square, LM, M square. Now one at least arrangement has to be remembered, and when you remember this, just simply copy this over here. So you get L square, LM, M square. Now here we are going to write these same terms, but just the negative of all these terms. So I am going to just attach a negative sign and write minus L square, minus LM, minus LM and minus M square. Whatever you write over here, same has to be copied in this position. So I'll have minus L square, minus LM, minus LM, minus M square. So this is the entire stiffness matrix that I have written. Here next I'll have U1, V1, U2, V2 raised to E is equal to P1x, P1y, P2x, P2y raised to E. So this is the entire EME. Now I'll start solving for element 1. The value of area is 100. The value of E is 200 gigapascal, which means it is 2 into 10 raised to 5 Newton per mm square. The length of the first element, as we have calculated, is 300. So I'll place 300 here. And now comes the entire matrix. So the value of L square is 1, M square is 0 and LM is 0. So when I write here, I get L square, LM, M square. I can very lightly make a cross sign over here. Whatever I write here, I'll copy in this positions, and whatever values I write here, I'm going to just take a negative of this. So minus 1, 0, 0, 0, whatever is written here has to be copied here. Here I'll write down U1, V1, U2, V2 raised to 1 is equal to P1x, P1y, P2x, P2y raised to 1. Now I'll solve this. On solving, I get a 10 raised to 3 outside, and the number which I have to multiply inside is 66.67. The rest of it is just copied from here. Now it is very important to mark the nodes over here. If you observe, my first element is between node 1, 2. The degree of freedom is 1, 2, 3, 4. So here I am going to write down 1, 2, 3, 4, 1, 2, 3, 4. This completes my EME for first element. Next I will go for element 2. My area is 100. E is 2 into 10 raised to 5. Length was 500. And then I have to write the entire matrix. The first value is L square, which is 0.36. So here I'll have 0.36. I'll have Lm, which is minus 0.48. Again Lm and then m square, so 0.64. So this is all I need to copy from the table. Rest I'll create on my own. Whatever I have written here, I'll copy at this end. 0.36 minus 0.48 minus 0.48, 0.64. Now, it is very important to be careful in this question, in this part especially, because now there are more numbers. Whatever number I have written here, just multiply with a negative 1 and substitute here. So this will be minus 0.36. This is 0.48. This will be 0.48 and minus 0.64. Just take it the negative of each value here. Whatever I have written here, I am going to just copy here. So minus 0.36, 0.48, 0.48 and minus 0.64. Here I have U1, V1, U2, V2 raised to 2 is equal to P1x, P1y, P2x, P2y. I am not going to change this. I'll just write here element 2. When I solve this, I get a 10 raised to 3 outside. The number which I have to multiply inside is 40. So when I multiply with each term, I will get 14.4 minus 19.2 minus 19.2 and 25.6. This is the first 4 elements. So I'll just copy them here. And negative of each term has to come here. So minus 14.4, 19.2 and minus 25.6. Copy the same over here. Copy the rest of the equation. Now element 2 is clearly between node 3, 4, 5, 6. It is between node 2, 3. So the degree of freedom is 3, 4, 5, 6. So I'll write over here 3, 4, 5, 6. 3, 4, 5, 6. Next I'll go for step 3, which is development of GME. For the stiffness matrix, I'll have a 10 raised to 3 outside. Now since the degree of freedom, the maximum value is 6. So I'll have 6 nodes over here. So I'll write down 1, 2, 3, 4, 5, 6. And here again I'll have 1, 2, 3, 4, 5, 6. Here I'll have U1, V1, U2, V2, U3, V3, because there are 3 nodes each having 2 degree of freedom, is equal to P1x, P1y, P2x, P2y, P3x and P3y. Now let's place the element. The first element is between node 1, 2, 3, 4. So I can just transfer these values there. So here again I have 66.67, 0, 0, 0. Element 2 is between 3, 4, 5, 6, 3, 4, 5, 6. And these are the values which I'll copy here. 3, 4, 5, 6, 3, 4, 5, 6. My value over here will be plus 14.4, minus 19.2, minus 19.2 and 25.6. Rest of the values will be 0. So here I have formed the GME. Next I'll go for imposing of boundary conditions. My variables are U1, V1, U2, V2, U3, V3. And here I have P1x, P1y, P2x, P2y, P3x and P3y. Now when I look at the figure, my node 1 and node 3 are shown as fixed. So I'll have U1, V1, U3, V3, all 4 as 0. At node 2, I can see there is a load of 2 kilonewton given in the downward direction. So let's write them down first. This is 0, 0, 0, 0. Here I'll write node 1 is fixed. Here again I'll write okay, you can either consider them as fixed or hinged. So I'll just write them as hinged, not fixed. P1x will be question mark, P1y will be question mark because these are the reaction forces here. Again, these are the reaction forces. So 2 more question mark. Since it's a 6 by 6 matrix, I'll have 6 equations. So I can afford only 6 unknown, out of which 4 are done. P2y is given as 2 kilonewton, which is 2 into 10 raised to 3 Newton, downward, so negative sign. Now if you observe carefully the second node, if it is moving downward, obviously it will not move in the x direction. So here I can say this is 0. Since I know these two values according to FEA, these two will be question mark. Now these are the values, so I'll go back to my matrix. I have U1 as 0, V1 as 0, U3 as 0, V3 as 0. Since these 4 are 0, for some time I will neglect first row, first column. I have second row, second column to be neglected. I have the last row, last column and second last row, second last column for some time. So these are the 4 elements, 2 over here and these 2. I have to find U2, V2, P2x and P2y are known to me. So I'll just quickly write the matrix down. Here I'll have a 10 raised to 3 common. On addition I get 81.07 minus 19.2 minus 19.2 and 25.6. Here I'll have U2, V2 is equal to, this is 0 and this is minus 2, 10 raised to 3 common. This will get cancelled out. My equation will be 81.07 U2 minus 19.2 V2 is equal to 0. And next is minus 19.2 U2 plus 25.6 V2 is equal to minus 2. When I solve these two simultaneously, I get U2 as minus 0.0225 mm and V2 as minus 0.094 mm. So these are the values of U2, V2. Now I'll go back to my matrix and calculate value of P1x, P1y, P3x and P3y. Now let's quickly write down the equation. I'll have only this term 10 raised to 3 minus 66.67 U2 is equal to P1x into 10 raised to 3. So I get P1x as 1.493 kilonewton. For the second equation, if you observe, all the values are 0. So even if you are writing the equation, no use. P1y is directly 0. Then I'll go for this equation. Here if I observe, I can see the third term and the fourth term. So minus 14.4 U2 plus 19.2 V2 10 raised to 3 common is equal to P3x into 10 raised to 3. On solving, I get P3x as minus 1.499 kilonewton, and for the last one, these two terms are present. When I multiply these two over here, I will get P3y. So it is 10 raised to 3 again, 19.2 U2 minus 25.6 V2 is equal to P3y into 10 raised to 3. P3y I obtain as 1.999 kilonewton, which is approximately 2 kilonewton if you observe. Last I'll go for my check step. Summation of load in x direction should be 0. So P1x plus P2x plus P3x is 1.493 plus 0 minus 1.4999. This is approximately equal to 0. And when I check for y direction, it is P1y plus P2y plus P3y. This is 0 minus 2 plus 1.999. This is also approximately 0. Hence I have checked my solution to be correct. After this, like previous numericals, we need to calculate the stress in each element. There is a formula for it. Sigma E is E upon L minus M L M into, okay, this is raised to E, U1 V1 U2 V2 raised to E. So let's solve for element 1. Sigma 1 will be 2 into 10 raised to 5. The length of the first element is 300. The value of L is 1, M is 0. So I'll directly write 1, 0. First node is between U1, V1, U2, V2. These two are 0. I'll substitute values of these two. I'll solve this, multiply inside. So I'll get minus 666.67, 0, 666.67 and 0. Here I'll have 0, 0, minus 0.0225 and minus 0.095 or 94, whatever you have obtained. So when I multiply, I get the value as minus 15. Now for multiplying this into 0, this into 0, this value into this number and this value into this value. So these two are to be multiplied and I get minus 15 Newton per mm square. Negative sign indicates there is a compression in this element. This is the value of stress for element 1. Let's go for element 2. Sigma 2 will be, again, E is 2 into 10 raised to 5, L is 500. Here I'll have 0.6 minus 0.8 minus 0.6 and 0.8. It is between U2, V2, U3, V3. These two are 0, U2, V2 I have just written. So when I multiply, I get the answer as 25 Newton per mm square. I think you can solve this. I get a positive value which indicates it is of tensile type. So this is how the numerical is supposed to be solved for a truss element. I hope you have understood the numerical. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to my channel. Hit the bell icon for latest updates of my videos. See you in the next session with another problem on truss element. Thank you.